Hello everyone, welcome to the notes for section 4.5 where we're still talking about exponential functions and logarithmic functions. We also have this other type which is called logistic functions, and we can use those sometimes, especially to model stuff like population, but we'll see some more details in these notes. And so I just want to get started with this first problem. We are given a little bit of data. We found out that in the year 2020, the population of Israel was around 8.7 million. And then we know that by 2050, it's supposed to grow to 12.7 million. So we could take those as being two data points. Now, instead of calling this the year 2020, if we're going to do what this problem says, it says that t should be the number of years after 2020. So if this is going t, and then I will call it p, this is going time, and then p is going population, then we know that whenever the time is 0, we should get, well, that's 0 years after 2020, so that's actually the year 2020. And the population is supposed to be 8.7 million. So we're doing population in millions is the y value, which I call p, and then the x value is the time that we call the t, and that's the year, how many years after 2020. So we get that data point 0, 8.7, and then we also get the one, let's see, in 2050, that's 30 years after 2020, so that's, the time is 30, and then the population is 12.7 million. So we have these two data points, and we're supposed to make an exponential growth model. We just understand that populations a lot of times grow exponentially, so it's appropriate to use this model. We don't have to get a bunch more data points because between 2 points, of course, we can just make a line, a straight line. This one's saying that we should make an exponential growth. So if we graph this, we have the year 0 years after 2020, the population is 8.7, and then after 30 years, we're in the year 2050, and the population becomes 12.7 million. So instead of just connecting these with a straight line, we're making an exponential growth like this one. And so this function should come out as a. This is going to be the population after, t years after 2020. This a naught, this should be the initial population. Always if you see a little subscript of 0, that means the initial value. And then it goes e to the kt. This k is the growth rate, which it will be as a decimal, but we could read it as a percent. So, it's going to be like 0.01, that's 1%. We just don't put a percent right here. We should put it as a decimal. And then t is the number of years after 2020. Now, the hardest thing in this problem is to find out what is the growth rate. What should be the number k right here? We will use these data points to find it. The easy number to find is this initial value, because that's actually already given to us. The initial value is 8.7 million, so that's what should go there. So our function is going to go a equals 8.7 million. I just want to write million. We're getting this in millions anyway, so we don't need to make it millions. 8.7 e to the kt. And in the year 2050, which we're calling with the t value 30, if we plug in 30 for t, we're supposed to have a population, which this will be our final population, this a, the population is supposed to be 12.7 million. So we can go 12.7 equals 8.7 e to the t is 30, and then k, we still don't know what k is. And so now we need to solve this for k. So we can divide both sides by 8.7, and then the 8.7s over here cancel. So we'll have e to the 30k equals, I'm just going to leave it as a fraction for now so that we don't round prematurely. It's safe to do this one. Now, whenever we want to solve for something that's in an exponent, we need to use logarithms so that we can leverage that power property. And since this exponential function is already base e, I would like to use log base e, which is ln, natural log. You have to take this function on both sides, the natural log of both sides. On the left side, this power now can go in the front, so it's going to go 30k. And it's going to go times ln of e. I'll still just write that one, but this ln of e, of course, is just 1, so it goes times 1 equals natural log of 12.7 over 8.7. And then we almost have k solved for us, so we just need to divide both sides by 30. These 30s will cancel, and we're going to get k equals, I'm going to get a number for this, but for the time being we have 1/30th, the natural log of 12.7 over 8.7. This would be an exact answer, but that is not very wieldy, so we're going to get, and that gives us a growth rate. Of course, this one's as a decimal, but we can read it as a percent. This is 1%. 1 point, how many decimals do we want? It was 0.0126. And so that is 1.26% growth rate, but our k value, will keep it as a decimal, the 0.0126. And so then our final answer, this function that we have, it's going to go a, we could also call it a of t, like this as a function. A of t goes 8.7 times e to the 0.0126t. Very good. And so anytime you see a function like this where it goes some number times e raised to a power, the coefficient in front of this variable is the growth rate, and you can read it as a percent. So you can tell from this one, if you're just given this function, that this has a growth rate of 1.26%. So now if we're trying to answer a question like this, in which year will the population be 10 million? That means that a of t, this becomes 10, is 8.7 times e to the 0.0126t. And we're trying to solve for t so that we can get the year. So here we need to divide by 8.7 on both sides. And I'm going to scroll down a little bit more. So now we're going to have 10 over 8.7. These 8.7s cancel, equals e to the 0.0126t. We need to get the t out of this exponent, so we've got to use this natural log again. This power right here is going to go in the front, so it's going to go on the left side, ln of 10 over 8.7 equals 0.0126t times ln of e, which is just 1. So I'm going to say that's just 1. And now we need to divide both sides by this 0.0126. Divided by 0.0126. On the right side is going to cancel, so we're going to get t equals, what do we have here, natural log of 10 divided by 8.7. And then we need to divide this whole thing by 0.0126. And so this is going to be 11. T is 11. 11 point something, but that means that many years after 2020. And so this should be the year 2020 plus 11 is 2031. So it's in the year 2031. The population should become 10 million. All right, now there's this new type of function that I was talking about, the logistic growth function. It uses an exponential function, but with a negative exponent in there, and that's in the denominator. And so you could think about what happens whenever t is going to infinity. This thing e to the negative t, this is approaching, you're going, imagine, I'm going to write it again, e to the negative t goes 1 over e to the t. So if we're plugging in big numbers for t, this whole denominator is getting very huge. 1 divided by a huge number, that becomes a very small number, so this is approaching 0. And so as the time grows, this number e to the negative t is getting close to 0, so it would end up canceling out this 5,000 e to the negative t. This would just go away, which means that this whole function, f of t, as t approaches infinity, this one is going to be getting close to just 100,000 divided by 1, which is 100,000. And so it's a way of making a growth function that has some maximum value. So if you drew this, it's growing exponentially at the beginning, but then it reaches towards its maximum, it starts to level off. And this is more appropriate for populations most of the time because populations at the beginning grow fast when they have no limiting factors, but as this population runs out of food, it can be running out of space, then it cannot just keep growing forever. And this one, it's not doing this for a population. This function is describing the number of people who have influenza t weeks after the initial outbreak. And I suppose it should be the people who have gotten it, period. So maybe this population has 100,000. The expectation is that basically everybody's going to get it at some point, but then you just cannot keep getting more people over and above what the population is. So let's see, how many people were ill by the end of the 4th week? This function is going f of t equals 100,000 divided by 1 plus 5,000 e to the negative t. And what is the meaning of t? It's t weeks after the initial outbreak. So by the end of the 4th week, we should plug in t equals 4, finding what is f of 4. It's going to be 100k on top, 1 plus 5,000 times e to the negative 4. And so we'll just have to get that in the calculator. 100,000 divided by, here parentheses are going to be necessary, 1 plus 5,000 times of e to the negative 4. That should be, I'm moving that parentheses to there. This looks good. So that should be 1,000 people. 1,080 goes 0.2. I don't know how much we should round this. Of course, you cannot have a part of a person, and so looks like about 1,080. I'll just round it to the nearest person. And that's an example of how to use the logistic growth function. But we can have a problem like this. What is the limiting size of the population that becomes ill? In other words, what is the maximum number of people that become ill as time just keeps going on and on and on? That's asking the question, what does f approach as t approaches infinity? That's the one that we were already looking at, this type of example. But as this number on bottom grows and grows and grows, we could graph this. We would see what the graph looks like, but what's going on in this denominator is that this whole term, this t value is getting very big, so you'd have something like 100,000 over 1 plus 5,000 times e to the, it can be 100 weeks or something. By the time you do this, 5,000 times e to the negative 100, this should be getting pretty close to 0. It's very close to 0. It goes 0.0, 40 zeros in a row, well, I guess 39 of them, and then a 1. And so this term is basically gone. It's going just 1 on bottom. And you'd have 100,000 divided by 1, which is 100,000. So the limiting size is 100,000. That's the most number of people that we would expect to ever become ill in this population. Now, we can choose appropriate models for data. We've got a lot of options by now because we've seen things like polynomials, we've seen now exponential and logarithmic functions, also logistic functions. Then there are rational functions. There are many types of functions, even ones that we don't cover in this class. But whenever you have some data, you should choose the most appropriate function to model the data, just based on what is the natural shape, what does it seem like it's going on in this data. So I'm going to make a scatter plot for these. I'm going to start 22 can be here, and then it's going by 5s, 27, 32, 37, 42 goes here, and then 47 is the last one. Now these percentages, they start on 9, and then it goes up, just barely goes up to 10, and then it jumps up to 13, so it jumps up by a little bit more. Let's say this is 10, so I was just below on 9, there goes 10, and then it jumps up a little bit more, 13. Here can be 20, 25, 30, 35. I'm going to run out of room. 40, 45, 50. Okay, so it's going to go up to 13, and then it jumps up to 20, and then it jumps way up to 38, is coming up here, and then it comes to 52, so it grows by a little bit less right there. What I'm looking at is how much these y values increase. Here it goes plus 1, here it goes plus 3, so the amount that it's increasing is increasing itself, plus 7. Then it goes plus 18 more, but then it slows down a little bit, the growth, it only goes plus 14. And so since these jumps are getting bigger, 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 that should be like exponential growth, but then the next jump is smaller. So if we come in here and we make a graph for these, it's growing like this, but then it seems like it's leveling off, it's doing one of these. And so this should be modeled appropriately by logistic growth. It's not to say that this is the only correct answer, because we still could match this by an exponential function that just keeps growing like this, but I think that the logistic matches it better, especially this last jump getting smaller. That's the one that is the most indicative for us, that it should be logistic. And then we have one more problem here we're going to look at. We'd like to rewrite this function. This is an exponential function. It uses some exotic base 4.6 to the x. Now, any exponential function that exists can be written with a base of e. And so the question is, how can we replace this 4.6? How can we write this as e raised to some number? I will write k, because always the other functions with base e, they were going e to the k t. This time we have x instead of t, but it's no different. X is the independent variable. K is this coefficient that is going to be interpreted like a growth rate. Okay, so if 4.6, we're going to write it as e raised to some power, and then that itself will be raised to x, and so the x will just multiply this one. We'll use exponent properties. And so what is it? 4.6 equals e to the k. So what is k? We need to solve for k. Well, of course we can do that by taking natural log on both sides. So we'd go ln of 4.6 is k times ln of e, which ln of e is just 1. So this just goes k times 1, which is k. And k is equal to the natural log of 4.6. Of course, that's the exact answer, but if we wanted to get just a number for that one, what is the natural log of 4.6? This decimal goes on forever, so we could truncate it if we want and just round the thing, but ln of 4.6, this is approximately 1.53, I'll call it. And so if we wanted to now, we can write this y equals 100. I will still leave it as ln of 4.6, so it can be the exact answer, but it's going to go e to the k. K is ln of 4.6, what we found. And then that goes to the x power. And so if we wanted to, we can just multiply these exponents, because that's what you do with exponents. The exponent rules say that we should multiply x times ln of 4.6. And I'm going to write it as x ln of 4.6. To me, it looks a little bit better having the x in the front. You could put the x at the end, but then I think you should put ln of 4.6 in parentheses, so you can tell that the x is not inside of the natural log function right there. But now it has the base, and actually I'm just going to write that as an example. E to the ln of 4.6, that's the coefficient, which we know is around 1.5, and then it goes times x. So e to the kt, as it were. This growth rate is big though, very big growth rate. It's actually more than 100%, 153% growth rate. But anyways, that's the end of 4.5, and I hope this video was helpful to you. I'll catch you in the next one. Thanks.